Today we're going to talk about calculating limits of functions or limits in general using the limit laws. There are a bunch of limit laws that I'm going to go through them first, then we'll do examples using these limit laws. Okay. Limit laws. Suppose you have a constant c and the two functions f and g, and you have the limit f of x as x approaches to a and the limit g of x as x approaches to a. In both cases, let's assume the limit exists and it's some number. Okay, then the following statements are all true. If they ask you to find the limit f plus g or f minus g at that value of a, then you can calculate the limit separately and add them up or subtract them. So limit f of x minus limit g of x as x approaches to a. If there is a constant multiplied by the function f, so limit c times f, you can ignore the constant, calculate the limit first, then multiply that constant later, c times limit f of x. This is just a linear behavior of the limit. If there is a product of two functions f and g, and you want to calculate the limit, you can calculate the limit first, then multiply them together, limit f times limit g. And this is all we're assuming that we're calculating limit at a, because generally we assume that the limit at that point already exists for both functions. If it doesn't exist, then you cannot multiply them together. Okay, if you're dealing with division, limit f divided by g, you can calculate the limits again separately and divide them by each other, but there's one restriction, that the limit of the denominator cannot be 0, otherwise you have an undefined fraction. What if you raise the function to some power? Let's say if you have f of x to the power 5 and you want to calculate the limit, you can calculate the limit of the function first, then raise the whole thing to the power 5. So this n as an exponent is a positive integer. If it's negative, then it will go to the denominator, and you have to make sure that the denominator is not going to be 0. And that's the only difference. If you have a constant function, so let's say you have a constant function f of x equals to 3. They have f of x equals to 3. And 3 is a constant c. So if you have this function, this is 3. The limit at any point at a is still 3, because this is a fixed value. It doesn't really matter how you approach to that value of x. The limit is always still that constant number. So the limit of a constant is always the same as that constant. If you're dealing with the function f of x equal to x, and they ask you find out the limit at a, the f of x equal to x was this 45-degree angle. The limit at a is exactly the same as the a value, because if you're approaching to a from each side, you're following along this curve. There's no arrow at the end. So you're following along this curve, and what you expect is exactly the value of a. So this is generally, by doing this, we can create polynomials. Limit x to the power n. 8 is a consequence of 5. If you have a function x, if you raise it to the power n, you can raise the other side to the power n. It's the limit that you can first calculate, then raise it to the power n. Okay. If you're taking a square root or third root or fifth root, doesn't really matter. You can operate that after you find the limit, but with the assumption that underneath the square root, if the root is even, or fourth root, underneath that is a positive value, non-zero, non-negative. If you have a function underneath the square root, you can calculate the limit first of the function, then take that square root or the nth root. Generally, it's true for the nth root. But if n is even, again, you have to make sure that the limit of the function underneath is positive or greater than or equal to 0. By adding all these properties and using them, we can say the following. We can say this is a direct substitution property. I'm going to show you an example. It says that if you have a polynomial as a function and you want to calculate, or a rational function, and you want to calculate the limit for that polynomial or rational function at a specific point, you can just simply replace that number inside the function. You could do this. You can find out what is f of a. with the assumption that a is in the domain. So if you're dealing with rational functions, it shouldn't make the denominator 0 because it would not be in the domain. We will get to this in a bit, but let's use these 10 properties. I made the law number 1 is basically 2 laws. So in textbook you will see 11 of them, but I made the one to be like a addition and subtraction together. I made it shortened for writing. Okay, so here use the limit laws to find this specific limit. Okay, by the subtraction property I can say this is true by saying this is limit 2x squared minus limit 4x as x approaches to 1. As x approaches to 1. I can break it up and to write it into two different limits. This is by the law of addition and subtraction, by the first law. And by the second law, which was a constant, I can write the constant outside. 2 times limit x squared as x approaches to 1 minus 4 times limit x as x approaches to 1. This is by the constant property. And now I can calculate the limits. Limit x squared as x approaches to 1. Here is the property. Limit x to the n as x approaches to a is just simply replacing a for x. So a to the power n. So I can say this is 2 times, I can replace 1 squared, minus 4 times limit x as x approaches to a, simply 1, replace 1. So what you get is 2 times 1 squared minus 4, it would be negative 2. And if you compare, if I ask you find out what is, if f of x equals 2x squared minus 4x, if I ask you what is f of 1, you can say it is 2 times 1 squared minus 4 times 1, which is simply negative 2. You see that these two are the same thing? This is a consequence of those laws and tells you that for polynomials, or generally rational functions, you don't really need to go through these laws and use them separately. You can just combine all those information and say, okay, I'm just going to replace the function, the value into the function. And shorten up the steps. You don't have to do these steps all over and over. You can just skip them and say, okay, I'm going to replace the value. And say f of 1 would be negative 2, so therefore the limit is negative 2. I can say, instead of going through this process, I can write this. 2x squared minus 4x. It would be simply replacing 1 into function 2 times 1 squared minus 4 times 1, which equals negative 2. But use the limit laws a couple of times before you jump ahead and do this substitution. And here, I'm going to do the limit law again, then we'll try to see if it works here as well. The limit 2 times square root of x, so it would be, I'm going to use the property of division, 2 root x plus 1 as x approaches to 4, divide by limit 5 as x approaches to 4. Again, I'm using the properties of law. This law of division, number 4. You have a function divided by each other, you can calculate the limits separately and divide them by each other. The numerator, I can write them as separately, as both inside. I can write this as limit 2 square root of x plus limit 1 as x approaches to 4 as x approaches to 4, divide by limit 5 as x approaches to 4. And now I can continue. The first part I can write it as, I can move the 2 outside since it's multiplication. I can write it as 2 times limit square root of x as x approaches to 4 plus limit 1 as x approaches to 4 divide by limit 5 as x approaches to 4. Okay, now here, at this point, if you look at the first part, you would have 2 times limit square root of x as x approaches to 4. This is using this property of number 9. You can just simply replace the a into the square root. In this case, a for us is 4. So I can say this is 2 times square root of 4. Limit 1 as x approaches to 4. It's a constant function 1. So it would be 1. Divide by limit 5 as x approaches to 4. 5 is constant, so again divide by 5. So what you get is 2 times 2 plus 1, 5 divided by 5 is simply 1. And you could have done, you could have calculated this without going through this process. Simply by replacing it here. And say, okay, I'm going to replace 4. 2 square root of 4 plus 1 divided by 5. It will be 5 divided by 5. Nothing wrong with it. The only thing is you haven't used those laws. Those laws are allowing you to do this. Okay. Try to do this a couple of times, then after a while you can skip ahead and ignore these steps. Okay. Now here I have an example just to show you that there is one more property for the limits that graphically it's easier to see, than I'll explain it through by writing the notations. Let's consider these two functions, f and g. The only difference between these two functions is this empty circle. The g function, f at 2 is not defined, but in the f function, f of 2 is 3. This is a closed point. So if I ask you the limit for the f function, and I ask you what is the limit of the f function as x approaches to 2. You approach to 2 on both sides of the curve. In this case, it's a straight line. What do you expect? You expect the y value to be 3. You don't look at that point. You look at the expectation. If I move along this curve, what do I expect to get? I expect to get the y value of 3. If I move along this curve, I'll expect to get y value. If you do it for g, what do you get for g? If I'm moving along this curve from low and above, what do I get is the expectation is that the limit must be 3 again. It's not the value. G of 2 is undefined. It doesn't exist. On the other side, f of 2 is well defined, and it is 3. But the only difference between g and f is that there is that point that the functions are not equal. That means here's this idea that if two functions, if f equals to g, almost everywhere, everywhere except, maybe I should say except at x equal to a. In this case for us a is 2. Then the limit of f equals to limit of g as x approaches to a. The limits are equal, but the functions are not equal to each other. The two functions are equal to each other everywhere except at this point. You see, that is enough for us to say that the limits are equal. It doesn't mean that the functions are going to be exactly the same. I mean, sometimes there's a hole in the graph. It tells you that the function of that location does not exist, but the limit still exists at that point. So here we use that idea for these specific functions. If you look at this function, x squared minus 2 divided by x minus 2, and I ask you to calculate this limit. If you replace 2 into the function and say, let's try to calculate by replacing 2. I'm going to do that first and use a different color. Let's replace 2. What do you get is 2 squared minus 2 divided by 2 minus 2. Numerator is 0, denominator would be 0. You should never say this is 1 nor 0. This is never true. Okay, so in this case, this is an undefined value. You cannot divide by 0. So what can I say about limit? Should I say the limit is undefined? Not really. I cannot say that. Because this 0 over 0 is if you look at exactly 2. We didn't look at around 2 to see what is the behavior of the function. We looked at exactly at 2, you get an undefined value. That means at 2, there may be a hole like this graph of g. There may be a hole in the function, but the limit may still be available. So what we can do is first, you can say, okay, this is not true. I cannot say that. So what I'm going to do is I'm going to rewrite the question. Try to simplify, to see if it's possible to simplify. Can we simplify? Let me write this one more time. If you factor the numerator, it's possible to say x minus 2, x plus 1. Here you have x minus 2 again, as x approaches to 2. If you cancel out the numerator and denominator, what you get is limit x plus 1 divided by x approaching to 2. Now what if you replace 2? You get 2 plus 1, which is 3. So the limit of the function, now you get 3. This is basically this example that I wanted to show you. The g function, g of x is x squared minus x minus 2 divided by x minus 2. On the other side, f function is x plus 1. And their only difference is at that specific location. At 2, this one does not exist. The other one at 2 exists, and it's 3. But the limits are equal to each other. So you can say, okay, in case there is this value of 0 over 0, if you have this is called an indeterminate form for the limits. If you have 0 over 0 in the form for limits, you can try to simplify it first, then calculate again. If you get a number, then you say, okay, the limit exists. If you don't get a number, then just say, okay, the limit does not exist if you cannot simplify it anymore. Okay, there is always, if you're dealing with 0 over 0, that means there is a factor that you can cancel out or something like that. We only focus on the ones that we can simplify at the moment. But if you have like sine divided by x squared or x cubed or something like that, there are rules that apply as well, that at some point we will use those. Okay, here's another example. At this point, if you're given this is a rational function, if you replace h with 0, what do you get? So if I'm going to write it here, first test. If you replace 0, what you get is 3 plus 0 squared minus 9. I'm replacing this h value of 0. Divide by 0, you have 9 minus 9, which is 0, divided by 0. This is undefined for value, but I can say this is an indeterminate form. Okay, that means for limit, maybe it is possible to simplify. So what I'm going to do is I'm trying to simplify the numerator first. 3 minus h squared would be 3 plus h squared would be 3 plus h times 3 plus h minus 9. In case you've forgotten, you can distribute, add them up. H approaches to 0. Okay. Distribute the numerator, you'll get 9 plus 6h plus h squared minus 9. Divide by h. See, the 9s will cancel out. What you end up with is limit 6h plus h squared divided by h as h approaches to 0. You can still continue to simplify. Numerator, they both have an h in common. Factor out that h. You get 6 plus h divided by h as h approaches to 0. You can cancel out these two. So what did I end up having is just 6 plus h. Now if you calculate the limit by replacing 0, you'll get 6 plus 0. And now you have a value for the limit. So what was the limit of this fraction? It's simply 6. There are shortcuts for this, but we will get to those later on. But here, at this point, you have to go through this procedure. If you're dealing with 0 over 0, 0 over 0, you have to simplify. Not always you get an answer, but if you simplify, you may end up with a good result. So this was an example of factoring or simplifying. There's square roots as well. You can use this for some cases. Here again, if you replace 3, first test. If you replace 3, what do you get? You get square root of 3 plus 1 minus 2 divided by 3 minus 3. 3 minus 3. What you get is 0 over 0 again. This will be square root of 4, which is 2 minus 2, 0 divided by 0. By the way, if this was like 5, and you calculate and say this is square root of, let me change this to 8. You'll get square root of 9 minus 2 divided by 8 minus 3. You will get 3 minus 2, which is 1. 8 minus 3, 5. This would be your answer. It's not necessary to simplify always. The only time that you need to simplify is if you end up with 0 over 0 in the limit form, then you have to simplify. In this case, 1 over 5 would have been the answer. So I'm going to go back and rewrite the question. I'm going to replace this limit with whatever it was. Okay, so now in these cases, when you're dealing with square roots, normally there is no way to cancel out. So what we do is we multiply by the conjugate. And hopefully in college algebra, you've seen the conjugate. But if you've forgotten this, it means you multiply the fraction or the square root, numerator and denominator, by the same thing. So if I multiply a 5 here, I should multiply a 5 here to create the same ratio. So what I'm going to do is not multiplying by 5, but I'll multiply by the same thing as I have in the numerator. Instead of minus, instead of the sign negative between, I'll use the opposite. If this was plus, I would use the negative. That's the conjugate of the numerator. So I'll multiply the conjugate of this radical term. Whatever I multiply to the numerator, I should multiply to the denominator. I'm going to do this step by step just to make sure everyone follows up. Limit x approaching to 3. Okay, let's multiply. I'm going to use red to multiply. You should distribute this times that, times positive 2, negative 2 times this, negative 2 times that. So what you get is square root of x plus 1 times square root of x plus 1. You'll get square root of x plus 1 squared. You get 2 of them multiplied by each other. Then square root of x plus 1 times positive 2. You'll get positive 2 square root of x plus 1. You get negative 2 times square root of x plus 1. So you get negative 2 square root of x plus 1. And negative 2 times positive 2 minus 4. And I'm going to write the denominator as it is. I don't need to simplify the denominator. I'm just going to write it as I can see it. There is no distributing necessity. I distribute the numerator so I can simplify and cancel out the square roots. But in the denominator, if you multiply, you're not going to simplify it. Okay, let's simplify the numerator. Limit. Okay, x approaches to 3. You see, here you see 2 root x plus 1, negative 2 root x plus 1 will cancel out. Squared and square root, you can cancel these. You'll get x plus 1 minus 4, which gives you x minus 3. Numerator, you have x minus 3. Denominator, there is an x minus 3. The whole purpose of this multiplying by conjugate was just to create this x minus 3 so you can cancel out these two. So what is left? I have limit. Numerator is only 1. Denominator is square root of x plus 1 plus 2. You may ask yourself that I didn't get rid of the square root, but that was not our purpose. The purpose was to get rid of 0 over 0. So now if you replace 3 and calculate, what do you get? Is 1 divided by root 4. I replace 3. 3 plus 1 plus 2. What you get is 1/4. This is the limit to our example. 1/4. Without simplifying, you could not get this number. Do not create table now. You have to use this multiplication and conjugate to get to this point. Okay, here there are some cases that we use piecewise functions. Absolute value is a piecewise function by itself. It's x when it's x is greater than 0, negative x when x is less than 0 or equal to 0 in this case. What does it mean? That means if you give a number here, 5, if that number is greater than 0, you'll get 5 as the result. But if you put a number like negative 3 inside, what do you get as the result is not negative 3, you get negative 3. That's why you have two pieces. Negative 3 becomes positive 3. That's how the absolute value function works. So if you're given, for example, a function f of x like absolute value of x divided by x, which you can rewrite always into terms of piecewise function, which is x, I can write the absolute value in terms of x, or I can write it in terms of negative x. Denominator is still x. Means I can write this in terms of x divided by x is 1, negative x divided by x is negative 1, x greater than 0, x less than 0. This is equal as well. Equal. Oh, no, sorry. At x equal to what am I saying? At x equal to 0, it's undefined. There is no equality. You cannot divide by 0, so there is no 0 equality. Okay, so in this case, if they ask you to find the limit as x approaches to 0, if you're dealing with piecewise functions, that means you have to consider both sides. This is something that you should be careful with. Piecewise functions around 0, if I approach 0 from left side or right side, it might be different. Okay, let's say x approaches to 0 from right side. What does it mean? That means you're picking a number close to 0, but from right side of 0. So if you draw the number line, this is 0, you're approaching from this direction. So what is that number is close to 0 from right side? Something like 0.1 or 0.01 or 0.001, doesn't really matter. So what do you get? You will get the x to be 0.001, which satisfies the top half of the piecewise function. That means the y value should be 1. So if I'm approaching 0 from right side for this function f, what do I get? I should get 1, because that is greater than 0 and it is approaching to 0 from right hand side. If I'm approaching from left side, the number that I'm approaching to is still 0, but I'm approaching from left side. That means the x value that I'm picking is somewhere close to 0, but it's smaller than 0. That means it satisfies the second second part of the piecewise function. What do I get for the y value? The y value must be negative 1. If the left and right hand side limits are not the same, remember that, then the limit totally does not exist. If these two were 1 and 1, then you would say the limit is 1. So be careful with the piecewise function. You have to see which part are you satisfying by picking that. If you're approaching, if they ask you what is the limit as x approaches to 3, close to 3 is always in the upper half of the functions. You don't need the lower part, so the limit would be simply 3. For the piecewise functions, be careful. Use this method of maybe drawing and picking an arrow using small numbers close by to see which interval or which part of the piecewise function are you satisfying. Okay. One last topic in this section is the squeeze theorem. It is maybe one of the important theorems in calculus for calculating limit. It helps with some cases that you cannot simplify. Squeeze theorem, sometimes it's called the sandwich theorem. It means you're squeezing a function between two other functions or sandwiching it between two other functions. So here, if you have f and g and h, 3 functions. You have these 3 functions, and the g function is between the 2 functions h and f. Not everywhere, but at least in a small area near a. So if you have h and f smaller and larger than g in a section of the curve or along this part that we care about near a, then what we can say about the limit? If you know the limit of f and h, if you know their limit of f as well as the limit of h, and you know that they are equal to each other and with some value L, what you can say is, you can think about it this way. You have a box, left side is L, right side is L. If I put a 5 here and 5 there and ask you, figure out what is this number that satisfies these two. There's only one option and not more than that. That option is 5. You cannot put 4 because 4 is less than 5, but it's not greater than 5. So the only thing that we know is if the upper and lower limit are equal to each other and they're both equal to L, then what can I say about the limit of the middle function? It's supposed to be exactly the same as those limits. These 3 must equal to same thing, 5. So what we can do is, in some cases, when it's not possible to use the limit laws, we can squeeze the function. And normally it's happening with when you're dealing with trigonometric functions like sine and cosine, because sine x and sine whatever, I should say sine theta, whatever theta is always between -1 and 1. Sine x, sine 1 over x, sine 1 over x squared, n over x squared, doesn't really matter. Whatever you put into sine function is always between -1 and 1. As well as with cosine, same thing holds, but not true for tangent and cotangent. So here, if you're given this limit of x times sine 1 over x squared, think about it this way. If I know sine 1 over x squared is between 1 and -1, what can I say about x times sine 1 over x squared? I multiplied an x here. To get to that, I multiplied an x. So I should multiply an x to both sides. I'll get negative x and positive x, or 1 times x. Negative 1 times x. That's what I did. So I know that the limit of this middle function is between x and negative x. I can say, okay, if I can figure out limit negative x as x approaches to 0, and then if I figure out the limit x as x approaches to 0, and if these two match, then I can say the limit is generally equal to that. So limit negative x as x approaches to 0 is 0. Limit x as x approaches to 0 is still 0. So it means both sides are approaching to 0 in terms of the limit. What can I say about the limit of this middle term? That should approach to 0. This is what we call the squeeze theorem. So I can say the limit of this middle function is simply 0. Again, this is normally used when you're dealing with sine and cosine, but there are other examples as well. Okay. Make sure that you use those limit laws and try to simplify. Do the homework. There are a couple more examples. I didn't get to pick all those examples and let you figure those out. If you had any questions, make sure that you contact me, ask questions. If I've made any mistakes in these videos, please email me so I can fix it, or make a comment so everybody else knows, so nobody gets confused. Okay, I'm gonna stop at this point.